All right, welcome everyone. So this is our third live stream geometry session. So for those of you watching, we've moved it from 7 p.m. on Thursdays to now 10 a.m. on Sunday U.S. Central Time. So I found that worked for more people around the world. So if any of you want to join, feel free to email me. So my email is in the description of my video. It's mgreenb801@gmail.com. All right, so we have Ram and Timo with us today. So Timo was on the live stream before. So now I will jump into the problems. So I'm going to share my screen. Hold on just a second. All right, can you guys see my screen?
Yes.
Yes.
All right. So I have not started solving these problems. I just took a quick look at the diagram to see that they looked interesting. But this is the first problem. So 1 second. All right. So we have a triangle ABC. And D is on AB. And E is on AC, and so that it's parallel, okay? And then F is the circumcenter of DEB. Hey, you're Joni. Good to meet you. Thanks for joining us. Irajan, thanks for joining us.
No problem.
Where are you from?
I'm from Kosovo.
Kosovo. I think
Yeah.
I had at least one problem on my channel from their team selection test. But good to meet you. Thanks. All right, so we're starting on our first problem. So we have a triangle ABC. D is on AB and E is on AC, so that DE is parallel to BC. Now F is the circumcenter of DEB, so I'm going to draw the circumcircle. All right, there's F, and then, whoops. And G is the circumcenter of EBC. Here we go. And we want to show that angle BAF equals angle CAG. All right. Let me try to make the figure look nice. That looks pretty good, I think, right? Let me check it's actually true. Yep. Yeah, I got this problem from a book. Have you guys heard of Geometry and Figures by Arsenia Kopion? You guys might not have heard of it, but it's a really good book.
Yes, I've seen that book. It has only figures, means lot of figures.
Yeah, it has only the figures. It doesn't have any proofs, any words of the problem statement. It just shows a picture of this. So that's where I got it.
I remember the cover, a goat cycling. That is the cover of the book, I think so.
Yeah. All right, so let's see. How do we do this? So I'm wondering if, let me try taking the midpoints of these, and then FH should be perpendicular to BD and GI is perpendicular to EC. Maybe we could show these triangles are similar. What I'm thinking.
We know DFB and GCE are similar.
What triangles? I'm sorry.
DFB and GCE.
EFB and GCE. All right. EFD. I'm sorry. So
FE and GCE. DFB and GCE.
all right. So yeah, we want to show that those are similar triangles.
We know that because DFB is 2 times DEC, and this is ZBE, and this is CGE half. So.
Okay. Actually, then this is a really quick one. So I'm going to just type out the full proof. But basically, we've kind of already solved it. So yeah, so unfortunately, this text thing blocks the diagram. So I'm going to move the diagram to the right. And then I'm going to draw the proof right here. All right, so let me move it even further to the right from him. All right, so here's how I'm going to write it. So we have angle DFB is equal to 2 angle DEB, which is equal to 2 angle EBC, and that's equal to angle EGC. All right. And so if that's true, then since DFB and EGC are isosceles, so I'll just write that. Yeah, I just like writing out the full thing just so that viewers of the channel can just explain it as we go through it. So and maybe the way I'm typing it out might be slightly different from the way you were thinking about it. So it's just to clarify this. And then if that's true, then that means that hold on just a second.
We can say BF over BD is equal to GC over CE, and then because DE and BC are parallel, we are done.
So BF over BD is equal to
proportional theorem.
GC over GE. Is that what you're thinking? Okay, and then yeah, now I see what you're saying. So since DE is parallel to BC, we have BD over AB is equal to EC over AC. And then we can combine the two. So if we multiply the two, we get BF over AB is equal to GC over AC. And then we also have angle ABF is equal to angle ACG, since those two isosceles triangles are similar. And so that means that triangle ABF is similar to triangle ACG. So that's side angle side similarity. And once we know that, then we get the conclusion. So angle BAF is equal to angle CHG. All right. Is that what you were thinking? Is that what you had in mind?
Yes, this was my idea.
All right. Sounds good. Thanks. Let me see. Is angle AFB always right? I don't think it is. No, AFB is not necessarily a right triangle. So you could have something like that, but yeah, then the whole proof would still essentially be the same. All right. It's a little tricky. All right, so sounds good. That was a quick first problem, so I'll move on to the second one. We could have root BC inverted. Thanks for joining us, I3435. Yeah, I've read a little bit about root BC inversion, and I know it's really useful. But unfortunately, I haven't done a huge amount of problems with it, so I'm not super familiar. But if you have a solution with root BC inversion, yeah, feel free to share it. All right. So point O is inside triangle ABC. Whoops, didn't mean to do that. Whoa. All right. Point O. And then we drop the perpendiculars to each side. D, E, and F. Yeah, GeoGebra doesn't have a way of doing altitudes. But yeah, I feel like they should. Okay, so then we draw the BC, CA. FD. You know, yeah, let me just finish drawing the diagram, then I might try to change it. So the perpendiculars from A and B to EF and FD meet at P. All right. H is the foot of the perpendicular from P to AB. You know what? I'm gonna relabel these points just because I like. I'm gonna make it so AB is the bottom side. So it looks a little nicer. There we go. So those two perpendiculars meet at P. All right, and then we drop another perpendicular from P to AB. And we call it H. And we want to show D, E, F, and H are cyclic. D, E, F, H is cyclic. All right. It's kind of interesting. O can be any point, and that's a cyclic quad. I'm just going to draw it. Yep. Yeah, there's like a lot of flexibility here because O is any random point. I wonder if O and P are isogonal conjugates. You know what? I think they might be. This is looking really familiar, actually. I think O and P might be isogonal conjugates. I guess I could cheat using GeoGebra and test it, but I'll just take it as a guess for now. Root BC inversion again. Huh. So I3435, you're saying root BC inversion means the problem is equivalent to showing O and P are isogonal conjugates? Oh, for the last problem. I'm sorry, my bad. So that's interesting. I guess it just so happened that there's an O and P in both this problem and the last problem. Oh, no, you're still saying O and P must be isogonal conjugates, but just not using root BC inversion. Okay. Because of a 6-point circle. I actually think I've seen that 6-point circle theorem in the book Geometry and Figures, but I don't remember exactly what it was. Let's see. So if we can show angle OBC is equal to angle PBA, then that would basically mean they're isogonal conjugates, right? That seems like it shouldn't be too hard. So let's see. Yeah, that should be an angle chase. So I'm going to write out the angle chase. But yeah, I think this can be solved using ideas about isogonal conjugates. I've never done any videos on this on my channel. But I've seen it a couple times pop up. So I'm going to write out the proof here to the left. Make some more room. All right, so let me see if I can move it far enough so that you can see the text and the figure at the same time. All right, I'll just stick with that for now. We know that top point is C. Okay, so basically, oh, wait a sec. Now I'm not sure how obvious it is. I was thinking it was an angle chase, but I was thinking O is the circumcenter, but it's not. So
I think it's an angle chase.
Oh yeah?
Because O, F, B, and D is concyclic, and so BOD is BFD.
Yeah, no, you're right. Okay, so it is an angle chase. So, whoops, sorry. All right, so we have angle ODB equals angle OFB is equal to 90. So ODBF is cyclic. All right, let me fix that a little bit. And so that means that angle OBD is equal to angle OFD, which is, I guess I'll just write it's 90 minus PBF, or 90 minus I mean, I guess I'll just write that it's equal to angle PBA. All right. So, and then we can use the same argument. So then we have angle OAE is equal to angle PAB. And so that means that O and P are isogonal conjugates. So I'll have to do a video on this sometime. But I think it definitely made this problem. I've seen something very similar to this before, so I feel like that's why I was able to recognize that quicker. But if I hadn't seen something similar, I don't think I would have figured that out as quick. Okay, so O and P are isogonal conjugates. And isogonal conjugates always have the same pedal circle. So I know Ram was just telling me earlier, maybe I should try to do problems that don't use as much advanced theory, but this one just so happened to. So if you know a lot about isogonal conjugates, it makes this problem easier. So basically that solves the problem because isogonal conjugates have the same pedal circle. So that means if you take the 2 points and you drop the perpendiculars to all 3 sides, they all lie on a circle. In fact, that's kind of what I-3435 is saying. So from there, it follows that, we'll just write it all out for people that aren't as familiar with isogonal conjugates. I'll just put by a well-known theorem. All right. And so that means that basically DEHF is cyclic. And in fact, the center of that circle is the midpoint of O and P. So that's it for this problem. All right, let's move to the next one, see if it'll be harder. So yeah, the next one I think is harder. So hold on just a sec. All right, so we have 2 circles that intersect at points A and K. One sec. But yeah, there is some work to show that isogonal conjugates have the same pedal circle from that last problem. So I didn't prove it in that video, but yeah, maybe I'll do it sometime on my YouTube channel. It's a really interesting theorem in my opinion. And yeah, it's not too complicated of a proof, but it's just interesting. All right, so we draw the common tangents. Now this is really interesting. So they only want the common tangent closer to K. If you delete one of the common tangents in GeoGebra, it deletes the other. However, you can just hide one of them, which is really weird. So I'm going to hide that one, but not this one. Okay, touches at B and C. Let me just hide the rest of it. All right, P is the foot of, so I'm actually gonna, I don't know, I'll just call the centers X and Y. Why not? Okay, P is the foot of the altitude from B to AC. Okay, so P and Q. All right. And E and F are the reflections of K over PQ and BC. Okay, so it would kind of be like you start with triangle ABC and then everything else comes after that. I guess is kind of what I3435 is saying. Let me just set everything up first. All right. So we call those E and F. So I'm just going to make a little more room here. So this is E. This is F. And we want to show A, E, and F are collinear. Oops. K is the Humpty point of ABC. What is the Humpty point? Is that like the, so I don't know if you guys have seen my video on the HM theorem, but it's like you take the perpendicular from the orthocenter to the median. Is that what the Humpty point is? Ah, okay. Uri John says yes. So K, that might be, is that like a I guess that's like a well-known theorem, that if you have like a common tangent and A is one of the points of intersection of the two circles and K is the other one, then K is the Humpty point. You guys are too fast. Okay. So A, E, and F are on the A median. Hold on a sec. Let me just try to process this myself. So I'm gonna draw. Okay, because this intersection point is the orthocenter. Oh no, we ran out of time. Oh no, we removed the 40-minute time limit. What? When was there a 40-minute time limit? Okay. Did you guys see that on my screen?
Yeah, it came.
But yeah,
is this a premium? Is this a like second tier Zoom thing? Like it's not free one, or are you paying for it?
No, it's free. I didn't pay anything to do this. So yeah, maybe I will have
Then
to eventually. I don't
then
know.
it should be like 40 minutes, but I think for today they are being generous for some time.
Well, I'm happy they're being generous, but yeah, I'll have to look into that. I'm glad the whole meeting just didn't abruptly stop. That's pretty nice. Okay, so basically, so D is the orthocenter, and if we draw the median, so I'm gonna let M be the midpoint of DC, and A, K, and M are collinear. So that's because the power of M with respect to both circles is the same, because MB squared is equal to MC squared. So M has to lie on the radical axis. So I'm going to write this all out later. Basically, A, K, and M are collinear. And then you're also saying that BK is perpendicular to AM. Let me see if I can think through why that is. Is that obvious? Well, that's the same as saying that this point, well, that's the same as saying AQKP is cyclic. So I'm trying to prove the theorem that you just mentioned, that K is the A Humpty point. Is it do you guys see, is there a reason why BK is perpendicular to AM? Maybe it's obvious, but I'm not seeing it right now. Okay, MK times MA is equal to MB squared. It's equal to MQ squared. And MQ is tangent. So, okay, so we're kind of using par of a point. Okay, so I'm gonna write this out in the end, but for now I'm just thinking through the proof. Okay, so AM is the median, and you guys are saying that E and F lie on the symmedian. So you're saying if you take the Humpty point and you reflect it over PQ and BC, then those points lie on the symmedian. I'm just trying to think through that, why that is. Yeah, I feel like it might be obvious I'm trying to think. So if you reflect K over PQ, then that new point is basically isogonal to K. So I know APQ is like inversely similar to ABC, but I'm trying to see from there how it would follow. Well, I think I kind of have an idea by doing an angle chase how we could show that. Okay, by symmetry, okay. So I think I kind of have an idea. So M is already the midpoint of BC, but if we take another point, oops.
I think we can use QM equals to MP because there are right angles in Q and P, and M is the midpoint.
Yeah.
So QM has to be equal to PQM.
Yeah, so QM is equal to MP, and not only that, they're actually both tangent to the circle through all these points. So X doesn't actually lie on that circle, but all these other points do. So MQ and QP are equal, and they're actually tangent to the circle. That was part of the proof that I3435 gave Actually, I don't even know if he used that tact in it. Yeah, he did. Okay. But that's the proof that K lies on the circle. I'm just trying to think through from there. So I'm gonna use what he said. So if we draw the circumcircle of ABC, so basically, if you guys have seen my video on the HM theorem, so it's way back in my channel. I think it might be like video 5 or something, but basically BDKC is cyclic. So for those of you that have seen it on my channel, this is a cyclic quadrilateral. And so if we reflect K over BC, then I kind of see how we can show that A, B, F, and C are cyclic. BKC is 180 minus, yeah, okay. So Timo just gave a proof that ABFC is cyclic. And then we want to show that F lies on the A median. And trying to think through that. I think it's true by symmetry. Okay, so I kind of see a proof why F lies on this median, because basically if AM hits the circle at another point G, then since basically since KM is equal to MF, but basically KM is equal to MF is equal to MG. So basically, yeah, so I kind of see that. So AM is the median, and angle CAM is equal to arc CG, and angle BAF intercepts arc BF, and it's clear that it's easy to see that those two arcs are equal. So I kind of see, why F lies on the median. I'm guessing it's like a symmetric argument to show that E lies on it. Okay, so there is, so I'm just going to write out a little bit of this. Okay, so I think I'm going to start writing it out. All right. Yeah, sorry to do this on the spot, but I feel like it's easier for the viewers to see the proof in action, sort of, rather than reading it in the description. Okay, so we have, so M is the midpoint of BC, so MB squared is equal to MC squared. So because those are both tangent, so that means M lies on the radical axis of the two circles. And then, so that means that A, K, and M are collinear. That's the first step. Whoops. And then now I'm going to show the proof that DK is perpendicular to AM. right. So we have a cyclic quadrilateral there. We want to show k lies on it. So I'm not going to draw in the circle yet, just because I don't want to make it look like it passed through k. All right. So and then, so it's a well-known fact. So we proved this in the last session on my channel. No, I don't think we did prove it. I think no. Actually, now I think we did. But so I'm just going to state it here. But MQ and MP are tangent to the circle through those 4 points.
Yeah, I figured out A, B, C, and F are cyclic.
Yeah, ABFC is cyclic. Yeah, that's Timo was saying that in the chat. Maybe you figured out a different way than him. So
if he proved it, then I'll continue from that.
I'm kind of, but how did you do it? Did you do like an angle chase or something?
Yeah, angle chasing, because angle BK, what is it? BKC is equal to BFC, because clearly F is the reflection of K. So I figured out that angle BFC is 180 minus of angle A. So that is pretty easy because
That's just an angle chase.
alternate angle chasing.
All right, so I'm going to write out all this stuff. So we have MB squared is equal to MK times MA, which is equal to MQ squared. So that means that K lies on that circle AQ DP. I'm just going to say by converse of power of a point, AQ DKP is cyclic. All right, and so now we can draw in that circle. Okay, so first I'm going to do what Sai said. I'm going to show that ABFC is cyclic. And I'm not going to do the full angle chase, but I'm going to write out the main idea. So we have angle BFC is equal to angle BKC, and that's equal to, and I'm not going to write out all the steps, but that's 180 minus PAC by an angle chase.
Yeah, it's pretty easy because angle KAB is equal to angle PBC because of the alternate segment, and since BC is tangent, and symmetrically same goes for angle MAC equals to angle QCB, I guess. Yes, QCB. So so these two angles, angle BAM and angle CAM, they combine to be angle A, and since PBC is equal to angle BAM, so
I see what you're saying. So
yeah,
angle KAC is equal to angle KCB, and angle KAB is equal to angle KBC. So from there, it's very easy to see. I almost want to write out the single chase, but I'm not going to.
No, it's pretty easy.
Yeah. So ABFC is cyclic. All right. And then I'm trying to remember how I did this. So we want to show, so angle BAF is equal to angle BCF. Trying to remember. Yeah, okay. So yeah, okay. So now it's just an angle. So I'm gonna write it out. So All right. So angle BAF is equal to angle MAC. And then, so that means that F lies on the AC median. And then we should be able to do the same thing with point E, right? Just thinking through it, but I think it's exactly the same idea, right? So if we took, really it's the same argument, because if we let KE, so E is a reflection of K over PQ, right? So let's see if nice. So, yeah, if we label the midpoint of PQ, they're kind of bunched up here, but E lies on the AC median by symmetry. Is it when you say by symmetry, it's like the same argument, right?
I wouldn't say it's the same argument. I would say we have AQP and ACB are similar, and K and F are the points with the similarity. And because K is the reflection of F on the line BC, and E is the reflection of K on the line QP, this symmetry means that QAE is equal to KAC.
Okay, so triangle APQ and ABC are like inversely similar, is what you're saying, right?
Yes.
And so K
And
lies
so the
on the
points in between them has to be similar in some pattern. So that's what, yeah, makes sense.
Okay.
Makes sense.
Yeah. So the whole figure APKQ is inversely similar to ABFC. Yeah, I'm just going to write it out like this, and then I'm going to move on to the next problem. So and so from there we have that since K lies on the median, since AK is the median, then E lies on the submedian. All right. Now I will move on to the next problem. But yeah, I learned a lot here. I didn't know that K was the Humpty point.
I think EQP is also similar to BFC.
EQP is similar to BFC.
Yes.
Yeah, that's true, because basically PQK is similar to BFC because they're the same parts of the figure, but then E is just a reflection. So yeah, that's a true fact. The tangent condition to K shouldn't matter. So let's see. So tangent closer to K. Oh, are you saying we just could have used the other tangent instead and the problem would have been true? Interesting. All right, I'll have to check that out after the session, but sounds pretty interesting. All right, so I'm going to move on to the next problem. Sorry about that. Oh, whoops, there's no problem here. All right. So let D be the midpoint of the base AB of isosceles triangle ABC. Let's do it like this. But AB is the base, so I'm gonna have to relabel some things. What am I doing? Sorry about that. All right, so I'm gonna hide the circle. D is the midpoint. All right. Choose point E. So E is any point on AB. And O is the circumcenter of ACE. All right. Center. All right. Call that O. All right, so we have three different lines here. So we have the line perpendicular to DO, the line through E perpendicular to BC, and the line through B parallel to AC. We want to show that they're concurrent. So yeah, I guess if I just draw it, then it would make it look like it's already true. But yeah, I guess just keep in mind that we have to actually prove these are concurrent. So we could take the intersection of two and try to show that the other one is true. I'm not sure how you guys want to do it, but I'm just gonna draw it out like this for now. All right, so how do we show? Is it easier to let F be the intersection of the two perpendiculars, and then we have to show BF is parallel? I'm gonna try that. Let's see. Just delete BF for now. Okay, so we want to show BF is parallel to AC. This feels like it might just be an angle chase. I'm sure you guys will see it very quickly. Is F the reflection of E over BC? No, doesn't look like it's true. But angle FBC would be 90 minus EFB. Hold on a sec, guys. I'll be right back. All right, I'm back. Let's see. Draw in triangle, the circumcircle ODF. All right. It goes through the foot from E to BC. Whoops. Sorry. All right, let's see. All right, so we have, I almost feel like, have any of you heard of orthologic triangles? I haven't used it very frequently, so that's sort of a more advanced idea, but when you have lots of perpendiculars like this, sometimes there's this like theorem with orthologic triangles that I feel like could come in handy, but I'm not going to use it here. So angle EFB, we want to show it's 90 minus angle ACB. And 90 minus angle ACB, trying to think if there's a nice way we could think about that. Let's see, we have two perpendiculars. Can we make an orthocenter somehow? You know what, I'm gonna try, let me do this just for the fun of it. I'm not sure if this is gonna go anywhere, but what if I draw the circumcircle of ABC and I draw the circumcenter of it? So G, so OG is perpendicular to AC and GD is perpendicular to AB. Just gonna draw that in there. Does that really do anything?
Can you draw the circumcircle of ODF again?
ODF, sure. Yeah, I'm gonna erase what I just did. Whoops. So yeah, OF is obviously a diameter. how would we use that fact? Trying to make it, okay, so yeah, how do I get B further away? I don't want to make it look like B lies on the, let's see if I make a, it's hard to make B not look like it lies on the circle. Let's see, how do I make B not look like it lies? I guess I have to make a very tall, skinny triangle to do that, right? That doesn't look super nice. Oh well, we'll just have to know that B does not lie on that circle.
Yes, you should remove it.
Oh, remove the circle?
Yes, it's of no use.
Hmm.
What were you saying about that orthogonal primer? that mysterious thing.
Oh, orthologic triangles. So it's like
Yeah, whatever that is.
you have two triangles where I'm trying to remember. I think it's like if you have two triangles, A, B, C, and A prime, B prime, C prime, and if you like take the perpendicular from A to B prime, C prime, B to C prime, A prime, and C to A prime, B prime, and they concur, then those triangles are called orthologic. I think that's what it is. And if one triangle is orthologic to the if triangle 1 is orthologic to triangle 2, then the reverse is also true. So it's a lot that I just said there, but yeah, you could look it up if you want.
Yeah, sure.
Yeah, I'll just type out the word for the viewers of this channel, but it's orthologic.
Can you draw the circumcircle of DEF?
Sure. Whoops. All right. So what made you think to draw that circle?
I had an idea, but I think the idea is not good. So
Are you sure?
I think you can erase the circle.
Right. I kind of like my idea of drawing the circumcircle of ABC just because, yeah, there's a number of connections, but yeah, I'm not sure. I'm going to try it one more time. Try drawing the circumcircle of ABC. Let's see if that does anything. I don't want to make it look like F lies on it. There we go. So are there any similar triangles we could do? We want to show that angle FBC is equal to angle BCA. So yeah, I haven't drawn segment CD, but obviously that's perpendicular. E. So if angle FBC is equal to angle BCA, then their bisectors also have to be parallel, right? So that's basically saying, yeah. All right, I'm gonna try something. Oops. So I is the midpoint of arc BC. Basically, we're saying BI should be perpendicular to AB. Oh no, what am I missing here? Oh, because F doesn't lie on the circle. I don't know, I was thinking that. So basically, yeah, so in that case, I should probably erase this. But if we take the angle bisector here, yeah, maybe I'll just draw that in. Basically, we want to show BH. So I'm just going to draw the perpendicular from B to AB. So basically, AH is a diameter, and we want to show that BH bisects angle BCF. Not sure how much this does, but let's give it a shot. So EF is perpendicular to these. I'm sorry, EF is perpendicular to AD. I'm just complicating the diagram a little bit, but let's see. So, I mean, EF is perpendicular to GI.
I think you should use the fact that O is the circumcenter of AC.
O is the circumcenter of ACE. Yeah. I feel like I have a lot of interesting stuff. Not sure where it goes though. Maybe we can use the angle bisector theorem. I'm making this really complicated, but Yeah, I'll erase some stuff if you guys want. Hold on. Yeah, I feel like there almost has to be an elementary proof of this problem, but yeah, I'm just playing around with stuff. Okay. I was going to try to use the angle bisector theorem on this, but I'm not sure if that does anything. Wait, is triangle HKB similar to triangle AHC? I think it might be true. No, I'm not so sure it's true. I'm just going to check it just in case. This is where I got to cheat using GeoGebra. Wait, is that the right? Ah, I think it might be. Huh. Let's see. So that's 62.5. Ah, yeah. How do I show triangle BKH is similar to triangle ACH? Oh, but yeah, that would be true if the problem was true. I just don't know if it's just as hard as showing the original problem. I think I kind of see it. Wait. Yeah, so I think I can show that triangle CAH is similar to triangle KBH. And I wonder if that kind of gets us there. Hold on just a sec. Okay. Is it confusing that the diagram is kind of complicated, or? Yeah, there's a lot of different things in the diagram. Hold on, let me just see if I can finish this thought for diagram would eventually get messy. Let me just try to think through this just for a couple more seconds. And if I can't figure it out, then I'll delete some of the stuff I did. So I can show angle CHA is equal to angle KHB. Then can I show yeah, I can show CHA is equal to KHB, but I don't know if that does much. Yeah, I'm gonna erase some stuff here. I still want to leave the circumcircle of ABC, but yeah, some of these extra points I'm gonna delete. Should BF be a tangent to the circumcircle? Sorry. No, BF, it intersects it at another point, it looks like. I might as well just leave that there. I'll be right back, guys. Hold on just a sec. All right, let's see.
Isn't OE tangent to circumcircle of BEF?
It could be. Let's check it out. Maybe you've already found it by an angle case. Let's see. Did you think OE was tangent? Is that what you were saying?
Sorry, I messed it up.
Oh, it's all right. This problem feels doable. I'm just, yeah, it feels like it should be. Let's see. I feel like there's got to be some similar triangles or something. So, yeah. So angle FEB is equal to angle BCD, right?
Maybe we can say F is the intersection of the line through E and B, and then we look at the reflection of F through point D, and we try to show OF is equal to O with the reflection point.
Okay, so basically we define F to be the intersection of these two lines, so that, and then we try to show that FD is parallel to OD. I kind of like that, right? That's your idea, right? So did you say reflect F over D?
Yes, this is, I think maybe this helps.
Okay, hold on just a sec. So if F prime is a reflection of F over D, hold on just a second. So basically AF prime BF is like a parallelogram, right?
Yes, and so C, A, and F prime are collinear.
Or collinear. All right. That looks kind of decent. So, and then, whoops, sorry. Let me hide this. Okay, so we want to show OD is perpendicular. So it's like, what if we had the circle? Like we'd want to show D as the midpoint of that chord. Maybe we could use like the butterfly theorem? I don't know. Like we want to show OF is equal to OF prime. I kind of like that. I feel like that gets us somewhere. Let me just.
Can you draw OF?
Yeah. Yeah, let me make F look, yeah, there we go.
Isn't OD perpendicular to F dash?
Yeah, that's what we're trying to show. If we can prove that, that would solve the problem. So basically, we defined F to be the intersection of the parallel through B to AC with the perpendicular through E to BC. So basically, the question says to prove that 3 lines are concurrent. So we let F be the 2 lines through E and B, and then we want to show that the other one also passes through it. So if we can show OD is perpendicular to FF prime, then that would solve the problem. Hey, John, I think there might, is there something going on in the background? John, can you hear me? Oh, hold on just a sec. Oh, it stopped. Okay. Yeah, so I like Timo's idea because I like how F prime, A, and C are collinear. So yeah, I'm just trying to see where we go from there.
Is it possible that triangles OEF prime and OCF are similar?
Oh, that could be. That sounds interesting. OEF prime and OCF. Let's check the angles. Kind of cheating here. 64.2, 71. I'm not sure. Let's check. I don't think so. Oops. What did I just do? See the chat. BF is tangent to the circumcircle of ABC. Let's see. No, I don't think it's tangent. It intersects it at another point. No, it kind of looks tangent, but there is another intersection point there. So it's not, BF is not tangent necessarily. I'm not sure how long we've worked on this problem. Do you guys know if it's been like 40 minutes? I think we might move on to another problem if it's, yeah, I still want to try at it a little longer, see where we can go with it. What if E is between A, D? Yeah, I kind of just assumed, let's see. Yeah, the problem's still true. But yeah, I guess I'm just assuming this one configuration for now, that E is between D and B. I feel like this idea has value. I'm trying to see where it can go. Using directed angles. Yeah, I mean, what I generally just like, so really you're right. Directed angles is the way to do it in all configurations so that you can have one proof that does all the different cases. But yeah, I just for simplicity, I just assume this configuration for now, just because I'm not super familiar with the directed angles notation, but yeah, thanks for bringing it up. This problem, I don't even remember. I think it might have been from Bulgaria Math Olympiad. I'm not 100% sure. I just found it. So Parmenides, so it has yeah. I mean, directed angles. It's like, yeah. No, you're right, Ramakrishna. They're useful. I just haven't spent enough time with them, but I probably really should.
Directed angles make some of the questions really simple because while directed angles, it's like more generalized for all the problems. Mod 180 degree is quite simple to work out in comparison to other methods of angle chasing. So
Yeah,
I prefer. Uh, so I was off beat for several minutes. Could you explain what is going on? What about the previous problem? Variable.
So this problem, we haven't gotten too much further, but the previous problem, I'll just pull it up just for you. Hold on just a sec. So the previous problem, so did you see this one? This had a fairly long period.
Oh yeah. The other one.
All right. Oh, hold on just a sec. But have you seen this one too? The one with Isogonal conjugates?
Yes, I'm talking about this one.
Okay. Yeah, I wouldn't.
Oh no. This one is already done. So
yeah.
Yeah, about that parallel thing. Yes, yes, this one.
So what we did was, this is Timo's idea. So let F be the intersection of the lines through E and B in the problem. So then we want to show that OD is perpendicular to DF, right?
Okay.
And then Timo said, reflect F across D to point F prime. And then we were able to show that C, A, and F prime are collinear. So we want to show that OD is perpendicular to FF prime. So that would be the same as showing that, since D is the midpoint of FF prime, that would be the same as showing that OF prime F is isosceles.
If we label the intersection of AEC and BC,
This point?
yes, is it possible that HF is equal to FB?
Looks like it might be. Let's see. Yeah.
And now we can try to show OHF is concurrent to OAF prime, and then we are done.
OHF and OAF prime is
and
so,
OAF prime, yes.
So OHF is like a really flat triangle, right? Is it that triangle?
Yes. And OAF
Ah,
prime.
I like it. All right. So, yeah, so we know one of the sides is equal, and we know the other side is equal. Yeah, that's probably just an angle chase. I think you got it. All right. So let's take it one step at a time. Okay. So, all right, I'm going to delete this and this. Probably even this. Okay. So yeah, I won't use directed angles right now, but maybe in later videos I will. So I'm just going to assume E is between D and B. Okay. All right. So first I'm gonna all right. There we go. Okay, so then let F prime be the reflection of F over D. Oops, I'm gonna add a little prime. And then now we could show that C, A, and F prime are collinear. It's not too hard. So so I'm just gonna write, so FB is a parallelogram. And so F prime AB, well, so yeah. I mean, once we know this, then yeah, we know F prime A and C are collinear. So I'm just gonna, so. All right. Save that. And then now we want to show that FH is equal to FB, like you mentioned. And let's see. So that's basically, if we could show EH equals EB, then since F is on the perpendicular through E, that would prove that. So, but EHB is isosceles by an angle chase. So, okay. So we have angle EHB equal to angle CAE, which is equal to angle EBA, which is equal to angle HBE. So oscillates, right? And so, and then we have F lies on the altitude from E to HB. So that means that, I guess the altitude is technically just doesn't go past the segment HB, but just write it like that. So then we have FH is equal to FB. Okay. And so I'm trying to remember, what did we do after that? Oh yeah, we wanted to show OAF is congruent to OHF. So, so we have HF equals BF, which is equal to AF prime, because FA, F prime B is a parallelogram. And then we also have OH equals OA. Okay, and then can we show the angle? So the rest kind of looks like an angle chase, right? Just thinking in my head how to do it.
I think we want to show that angle FHO is equal to angle F prime AO.
Yes. Yeah, we want to show those two are equal. So FHO, I'm trying to think how to, of course there's different configurations. I'm just going to do it with the configuration in the diagram, but yeah, these directed angles, you could probably do all of them at once. So I see a way to do it. This might not be the fastest way, but this is how I'm going to try to do it. So angle FHO is 360 minus angle FHB minus angle EHB minus angle OHE. Let me see if there's a better way, actually. I'll just write that out for now. So actually, let me just write it like this. Minus angle FHE. So I'm just going to combine two of those. And angle FHE is equal to angle FBE. And yeah.
Yeah, FBE is 180 minus BAC, and
Yeah.
OHE is HEO. And then I would say we can say HEO is 180 minus OEA minus BEH.
Okay. So whoops, sorry. Okay. Plus. So, and then angle OHE is equal to angle OEH. Wait. And OEH is like 180 minus OEA minus HEB. Okay, so plus. Um, okay. Whoops. So it's like that. So 180 minus OEH. Well, OEH makes 180 degrees with OEA and HEB. And then OEA is the same as OAE. Yeah, I'm just trying to see. Yeah, it's really, I mean, I'm sure it's just an angle chase from here, but.
Now we have BEH is ACB and OEA is EAO.
Okay, whoops. Why does it do that? It drives me nuts. Okay. Yeah, let me try this. I'm just trying to copy that one thing. Let's see. I'll just write out again. BB plus angle OEA plus HEB is the same as ACB. And then CAB plus ACB is just like 180 minus CAB. Uh-oh, I should change that to OAE like you said. Yeah. So yeah, from here, I'm just gonna it's not hard to show that this is 180 minus angle OAC. So I'm just going to leave the rest of that calculation at the end. And that's equal to angle OAF prime. So triangle OAF prime is congruent to triangle OHF. And that means that OF prime is equal to OF, which means OD is perpendicular to F prime F. And that's since F prime D is equal to DF. Yeah, this is a really cool solution. I like it, Timo. All right. So thanks a lot for that. So let's see. We are almost 2 hours into it. I'm going to pull up at least one more problem. Let's see. Oops. Sorry. Well, have a good one, Timo. Thanks for participating. Yeah, that was a really nice idea. I agree. Oops.
Yeah, thanks that I can participate.
Yeah, thanks. Have a good rest of your day.
Thanks too. Bye.
See you. All right. So I will go to this problem. I think is pretty tricky if I remember. I think this is the only other problem I have though. Let's see. So this is the last problem we're going to do today probably, but I'm going to pull it up.